Good morning, everyone. My name is Ganga Meghnath. I am a second year master's student in ECE, and today we'll be going over my project, Diffusion-based generative models for image synthesis. Now, during the course of the project, I reviewed these three papers, and for implementation purposes, we'll be focusing on denoising diffusion probabilistic models by Ho et al. Now, what are diffusion models? You can break it down to basically three components of a markup chain. First of all, it's forward diffusion process, which involves scaling down the image and adding fixed amounts of noise with fixed amounts of variance. All right. That is, you go from input image X naught, scale it down, add noise, scale it down, add noise until you get a wide Gaussian noise XT. Now, turns out because these are all Gaussians, right? You can write it in closed form such that given any input image, you can get xt at any time step t with just a single Gaussian epsilon. All right, now what is reverse sampling? Reverse sampling involves actually going from a noise back to the image. Now, how do you do that? Turns out you can kind of reverse this process, and for small amounts of noise, the reverse probability distribution is also a Gaussian, and you can sample from this Gaussian using Langevin dynamics. But the thing is, you need the noise that is added in the forward process. Now, how do you get that? We use a deep model, which is a noise model. Here we use a unit that is aligned with the original diffusion models paper. Now, given any xt that can be sampled from a forward diffusion process, we try to learn the noise that it actually added to x naught at time step t in order to get xt. All right. Okay. Now, what are the three key takeaways I got from this project? One is that weighted L2 loss, when clipped, contrary to what the original authors are saying about it being unstable, I found it stable when I clip it, and I actually got better results, better image quality with weighted L2 loss than just using vanilla L2 loss, which is what they used in the paper. And second, I found that interpolation in the latent space, as you go deeper into the markup chain, higher T's, basically when you sample back into the visible space, the interpolation is not very smooth. And lastly, you increase the length of the markup chain T. Yes, the inference time is longer, but you get better sample quality. Now, for evaluation, we do use common GAN metrics such as FID and inception scores. But since these are not, inception is not exactly trained on data sets like MNIST and Fashion MNIST, we also use custom trained CNN classifier and define our own FID and IS and class label wise SSIM and RMSE scores for our data sets in order to measure sample quality performance. Now, coming to the data sets, we use CFAR10, Fashion MNIST, and MNIST. Now, this is a demo of the forward diffusion process which we get. You can see that the image is being scaled down, added noise, and ultimately we get a wide Gaussian noise. Now, depending on the complexity of the image, you can see I had to use a higher T for a complex data set such as CFAR10 as opposed to a simple one such as MNIST. Now, this is what we got from our implementation after we had trained a noise model. You can see that we are able to generate images from noise. Now, coming to experiments, from what I see, if you increase T, as you increase the length of the markup chain, you get better quality images. And also when coming to the loss functions, I tried out all of these and I found that L2 weighted loss with clipped weights between 0 to 1 gave me best performance. And turns out this clipping is very crucial because this clipping makes the training stable. And if I go to anything above 1, the images generated are very poor and basically the training becomes extremely unstable. Now, lastly, I did try some variance initialization techniques. I tried linear, cosine, quadratic, and sigmoid, but it didn't seem to have much effects. And coming to interpolation, I did try interpolating in the latent space. So at each T, you try to kind of do convex combination of these two images. I try to go from a shoe to a shirt, and I saw that, well, basically, if you go into deeper, higher T's, XTs, the interpolation is no longer smooth. Initially, you see from shoes to shirt, but then it kind of, because of the high variance in your sampling process, you kind of lose meaning and you do arrive at the image manifold, but you don't get a smooth interpolation. And well, that's it for my presentation today. I hope you liked it. Thank you.